The second complication that can occur in optimization is when a vertex is on a dotted line, which means there's an inequality with just either a greater than or a less than sign. It doesn't have the equals as an option. So this means the vertex itself is not included in the solution set, so it can't be part of the answer. However, a point close to the vertex could be the answer. We solve this problem just like we did for vertices that are decimals. Find a point near the vertex where x and y are both whole numbers and either in the shaded area or on a solid line. Use that point instead of the vertex that's on a dotted line. Let's look at an example. A coffee shop sells tea and coffee according to the following constraints. Each hour, the shop must sell fewer than 10 beverages. They must sell at least one tea, and each hour, the shop sells at least as many coffees as teas. The coffee shop earns a profit of 75 cents for each tea sold and $1 for each coffee sold. How many teas and coffees must the shop sell each hour in order to earn the maximum profit? We start off, as always, by defining our variables. We let x be the number of teas sold each hour, and let y be the number of coffees sold each hour. Now we need to translate those words into inequalities. Each hour, the shop must sell fewer than 10 beverages. So that means x plus y will be less than 10. When we rearrange that into the y equals ax plus b format, we've got y less than or equal to negative x plus 10. Each hour, the shop sells at least one tea. So x is our variable for t. X will be greater than or equal to 1. Each hour, the shop sells at least as many coffees as teas. So the number of coffees, y, is greater than or equal to the number of teas. So the number of coffees could be equal to the number of teas, but it could also be greater than, right? It's at least as many, so that's the minimum, but it could be more. And then we have our final two constraints of the two axes, x and y axes. So the y-axis where x is greater than or equal to 0, and the x-axis where y is greater than or equal to 0. Let's go ahead and look at the graph of these inequalities. The green line represents y less than negative x plus 10. The red line represents y greater than or equal to x. And the blue line, or the purple line, represents x greater than or equal to 1. Since x is greater than or equal to 1, we can see that the shading was going to be on this side of that line. In the case of y less than or equal to negative x plus 10, it's a dotted line. So it's everything up to but not including that line. And because it's less than, it means it's going to be under that line. And in the case of y greater than or equal to x, we can see that again it's going to be above that line. So when we look at that, it's pretty clear that the shaded area is what's shown here in green. Now we need to find the coordinates of each vertex. Let's start with vertex A. It's the intersection of the lines x greater than or equal to 1 and y greater than or equal to x. We go through the process as always. We take the two lines, we change them into equal signs so that we've got equations rather than inequalities, and in this case we're going to use the substitution method to solve. So it's fairly straightforward to get vertex A is 1, 1. Looking at vertex B, where we've got the intersection of x greater than or equal to 1 and y less than negative x plus 10, we go through again the same process. Again, we can convert both inequalities into equations and use the substitution method again to solve. So in this case, we can go ahead and take the 1 from here and substitute it in for x. So we get y equal to negative 1 plus 10, so y is 9. However, this is where the issue of the dotted line comes into play. Because we've got a dotted line here, we can't actually go all the way up to 9. So we have to go to the point that's closest to it, and in that case we can go to 8. You can see here on the graph we're actually using two spaces to indicate each one, right? So here is 9. So we need to back up to 1 point to 8 to claim that vertex. Looking at vertex C, similar situation. We've got the intersection of the dotted line, so y less than or equal to negative x plus 10, and y greater than or equal to x. I'm going to use the comparison method in this case to solve. So we're taking the negative x plus 10 and the y equals x, putting them equal to each other, solving for x. So we end up with x equals to 5, and we can substitute that back into this equation that says if x equals 5, then y is 5. So we come up with a vertex of 5, 5. However, points along the dotted line are not included in the solution set, so we need to pick a point that is the next closest valid point. To do that, we go back to this case. We can look at 4, 4, or 4, 6, or 4, 5 is actually a little bit closer. So we're over 4 and up 5, and then that becomes our solution. Step 7 is to identify the target objective and write the optimizing function. The target objective, we were told, was to maximize profit. So we're looking for the maximum profit, or the highest value for profit. So our optimizing function, we say profit is equal to, and then we're told that they make a profit of 75 cents on tea. So it's 0.75 times the number of teas sold, 0.75x, and they make $1 for each coffee. So it's 1 times the number of coffees sold, or 1y. So that's our optimizing function. Now we use that optimizing function at each vertex to calculate the profit. So we take vertex A, substitute 1 and 1 in for x and y, do the calculations, and we end up with a profit for each one. We repeat that process for vertex B and vertex C, and we come up with a profit for each. Now we can look at each of those and ask which one gives us the maximum, and fairly easy to see that 8.75 is the largest profit value that's available. Now we just need to answer the final question that was posed in the initial problem, and the answer is the shop must sell 1 tea and 8 coffees each hour to earn the maximum profit. Try the next question on your own, then come back to watch the video segment to check your answer and watch the solution.